This is our final presentation for the ping pong ball launcher. Our group consisted of Jack, Logan, Will, Delaney, Jaron, and Kelsey. We were all in charge of different subsystems for the ping pong ball launcher. We all had different levels of experience prior to this project and divided up the sections according to which portion we were most comfortable managing. Jack was our group leader and oversaw the rotational base portion of the ping pong ball launcher. Logan oversaw the final system integration portion of the launcher. Will oversaw the vision system for the launcher. Delaney was in charge of uploading the important documents into the Google Doc and the scoring structure. Jaron oversaw the aiming code portion of this project. And Kelsey was in charge of the ping pong ball launcher and taking meeting notes during our weekly meetings.
The goal of this project is to create a game for children with disabilities where they can aim and launch a ping pong ball at a target with the press of a button. The target should be no larger than 1 foot in diameter, and there should be an indication of whether or not the child scored. The entire game should take no longer than 4 minutes to assemble. The production cost should be low. The game should also fit within the provided cardboard box.
Now we are going to go through each of the individual designs for each subsystem. This was the 3D model of the ping pong ball launcher that we all decided on creating with all of the dimensions of important parts and with all the radius of the circles and the lengths measured. This was the prototype of the ping pong ball launcher that we created. We initially were going to laser cut wood pieces to make our prototype, but because the Innovation Center was closed, we had to make use of what we had in our houses. So we just made the tube out of a toilet paper roll, along with the spring that we were given earlier in the class. We selected this ping pong ball launcher through first looking at the requirements of the device outlined in the project requirements. We knew that the launcher had to launch a ping pong ball 2 to 4 meters within a 1 foot diameter of the target. We also knew that this device needed to be consistent and not take too long to construct. We researched similar designs and compared them to our needs, and then each group member drew their own sketch of the ping pong ball launcher, and those are pasted below. Jack then created a decision matrix to analyze all of the different designs. We all agreed on the numbers given and set the weights for all of the criteria. After doing this, it was very evident that the last design was the best design for this project. The challenges we faced were deciding how we were going to build this given the time frame. None of us are skilled in laser cutting wood, so we had to decide if the design would be worth it. But overall, we decided that the design would indeed be the best for the lowest price. We learned that it takes a lot of planning and justifying to pick a design. It does not work if you just pick the design you thought of. We learned that designing takes a lot of considerations and opinions to make sure that you are building the best design that you can. And pictured to the right is the design that we decided to go with, and above that is the decision matrix that was created. As of now, we have a very simplified prototype built consisting of a toilet paper roll tube, a compression spring, and a ping pong ball. With the current build, it would take about 10 seconds to put it together because it is a very simplified version of our original build. With our current build, our launcher is made out of materials found around the house. We are able to integrate the system because each group member has the required materials to put them together even though we all built them separately. The future steps that need to be taken would be to build the actual build that we intended to build, but we are unable to laser cut the wood pieces and put them together due to the Innovation Center being closed.
Hi, my name is Jack Rouch. I am in charge of the rotational base for the ping pong ball launcher project. Starting with the 3D model, I have the drawings of the rotational base here. On the left, I have the top of the rotational base. This hole will go through the axle, will hold the axle, and where that will hold the ping pong ball launcher itself. On the right, I have the bottom rotational base that will rotate everything, including the launcher. On the next slide here, I have the schematic. I have 2 servos being powered by 5 volts and going to ground, and 2 digital ports that goes also to the servos. On the next slide, I have the pictures of the prototype. For this prototype, since we were limited to what we had in our house, I had a Google Home Mini that was given to me by Spotify for being a Spotify Premium member, and I looked at it and thought it would work well for what we were using it for. So built it together, used some staples and some tape to put it all together, and it rotates on the piece that would protect the Google Home Mini. So was able to do that at free of cost. On the next slide, I have the concept selection. We were able to choose what rotational base we wanted to go with by using a decision matrix shown at the bottom. The criteria that we used was an even weight, agility, material we had available, the time frame that we were given, and budget. Based off of the given criteria and the weight, we decided the design 2 was better. Some of the challenges that we had for this was knowing that we were not going to be able to use the Innovation Center. And a lesson that we learned was that just by using household items, we would be able to come pretty close to what we needed to do. For this next slide is the future steps of the rotational base. The current status is a prototype without any electronics. So to be able to integrate, we would need to add the gears for the base to rotate on and the motors that would power the gears, and a program to be able to know a program that would tell the gears and motors where to move. Estimated time for this was 2 to 3 hours of adding the electronics and cutting the gears in the Innovation Center, or maybe with just cardboard around the house, whatever would have to be done, or something like that, and 2 to 3 hours of programming and debugging just to get everything right. And that is the rotational base subsystem.
I was in charge of the scoring structure. This is my drawing, and this is the 3D model that I created. Originally, we had 3 ideas. The first was a target similar to a dartboard. The second was similar to a basketball hoop. The third was a box. We decided not to use the dartboard target because it would be really hard for a sensor to determine if the child scored or not, as the ping pong ball would just bounce off. We decided not to use the basketball hoop target because if the ping pong ball didn't fall directly in front of the sensor, it wouldn't register that the child had scored. We've ended up using the box idea, but we've changed it in a lot of ways. We put the fiducials on flaps on the side of the box. We added a hoop with a 1-foot diameter for the ball to go through. And instead of tilting the box forward towards one corner for the ping pong ball to roll into, we added a little ramp so that the ping pong ball would land on the photo transistor. The box idea was also the most cost-effective because the cardboard box was provided for us. The biggest challenge we faced was having the sensor reliably detect when the child had scored. One lesson we learned is that no idea is perfect and that you have to keep revising your idea throughout the entire project. This is the prototype I built before classes moved online. There's a link to a demonstration video that shows me throwing the ball through the target and falling onto the sensor, and then the light turns on. Schematic for the circuit and my scoring structure. As you can see, the photoresistor is connected to power and to ground, and the photoresistor is actually connected to longer wires, and it's placed inside of the box at the bottom of the ramp so that the ping pong ball covers it up. Then there's another part of the circuit that's connected to a red LED and a transistor. The red LED is told to go off by the code I wrote. The LED goes off once the photoresistor is covered by the ping pong ball. meaning that the child scored. Currently, we have a 3D model and also a fully built prototype. The only part of the scoring structure that is an interface between subsystems for system integration is the fiducials. System integration would mean that the fiducials can be easily picked up by the camera for the vision system. This shouldn't take very long to make sure that it works. I estimated 2 days in case there is a problem and it takes a little while to fix it. If there's a problem with the fiducial flaps, I hypothesize that it's because the flaps that connect them to the box are too long. The flaps on the prototype that I built move a lot, and if we made them more stable or maybe even change what they're made of, it would prevent them from moving and they would be more stable, which would improve the interface with the vision system.
This is Will Mikauskis, and for my portion of the project, I had the vision system. And the role of the vision system was to take a picture of the target and determine where the fiducials are and how far apart they were in a real-world measurement. So, for my first slide, I had the flowchart of the code that would be able to identify where the fiducials are and create an image which is all black except for the fiducials, which are white circles. And then it would be able to determine how far apart those fiducials are in a real-world measurement. And once these calculations have been made, then they can be sent to the aiming code so that the launcher can be aimed appropriately. And for the next slide, for the concept selection, I gave the 6 different options labeled A, B, C, D, E, and F that my group decided on. And for the next concept selection slide, I showed the decision matrix and how we decided to go with goal B because the fiducials on this one were getting picked up the easiest by the camera, which gave us the highest probability of our code working out properly. And then for the final slide I had, it was the future steps, and it described the current status of the code, which is just taking the image and making it completely black except for the fiducials, which are white circles. And then to integrate the vision system, we would need to combine the final code with the aiming code so that our launcher would be able to identify the target, see the fiducials, determine what angle it needs to be launched at, and then finally launch the ball. And for this to be done, it would take probably 2 to 3 hours to combine the code and test it out and debug anything that happens that would be detrimental to our final design.
Our aiming code works hand in hand right with our vision system code. So our vision system isolates the fiducials and determines the distance between the fiducials and the launcher in the horizontal and vertical axis. It will then determine the angle that we need to raise the barrel of the launcher at. The aiming code uses that data to move the launcher however it's supposed to be moved, whether it be rotating the base or lifting the launch barrel, and so on. And then at the end of our flowchart, you can see that the launch is initiated by the user. This will activate a servo motor that will release the ball and whatnot. So our flowchart also treats the vision system code as more of a function, just because when you're looking at the aiming code, you want to use the vision system as something to gather data from, rather than having all the code together at the same time. Yes, they really work hand in hand with each other when it comes to using the camera to determine where the ball needs to be launched. In the future, we obviously want to create more of the code based on our flowchart, but well, no, that's really it. But we also want to make the code user-friendly because somebody that would be using this would not necessarily have the coding experience to just change the variables or replace data, whatever needed to be done. So we need to create a user interface that would allow somebody without that experience to work the launcher in any way they needed to.
System integration. As you can see above, we were able to get somewhat of our final design completed. It didn't turn out exactly how we wanted it, but it is something. Pictured to the right is the scoring structure that we just used as a box and placed fiducials on the outside so the camera can pick it up at the target successfully hit. Pictured on the left is the launcher integrated. We used a circular base with a square base placed on that so we could feed the axle through the hole in the square base. We then fed the axle through the launcher, but I couldn't get that to fully work on the CAD software, but I got it as close as I possibly could. Concept selection. As you can see here, you have the scoring structure along with the launcher and the camera on top of the laptop. This was the first design solution that we came up with to integrate all of the parts together. We already have the target and the scoring system put together, so we really only need to be able to get the launcher onto the base and get it to rotate, and the above sketch is how we plan on doing that. First cut of design. In the first cut of the design, instead of going with a more square base as depicted in our first possible design solution, we decided to go with a circular base to give the launcher a more even ground to sit on. The launcher is placed in the dead center of the base and can rotate around to accurately hit the target. As you can see in the drawing, the launcher is placed on a circular base with the square base on top of that, and the launcher is resting on the axle. Future steps. In the future, I would really like to get the chance to actually integrate the system as a whole. Right now, it's hard to integrate just a toilet paper roll and a ping pong ball and place it on a base to launch. I have really, however, enjoyed working on the CAD software to try and put our CAD drawings together. But I feel as if we were still on campus getting to use the Innovation Center, we could come up with something a lot better than what we have right now. I would like to have a better background in the CAD software if this was to ever happen again, because I feel like it is more complicated to put together online than it would be to put together if we were all on campus. This has been a great practice for future jobs, however, getting to work on the CAD process to design things.
This slide shows the economic costs for our project. On the left, there's the hours that each person worked and how much they cost per hour and the total cost for each person. On the right is our bill of materials, so this includes which materials we used throughout the project and how much they cost. The bottom right shows the total cost for the entire project, and it's a little over $10,000. This slide shows our project's Gantt chart. As you can see, we're mostly finished with the project, but there's still a good amount of gray left. The unfinished part of our Gantt chart represents the demonstration portion of our project, which we were unable to complete because coronavirus caused our course to move online. Despite this setback, our project is still complete through the peer review stage.
With our engineering judgment, we think that our overall design is really good. We were able to show our device and justify each decision that we made. We were able to use calculations to also show why our prototype should work. Our design was developed through the use of the engineering design cycle, and we listened to the suggestions of others through the peer reviews and revised accordingly. We have put in a lot of time and effort into making this design the best it could be with the materials that we have around the house. The biggest risks that we have moving forward would be to actually build the final product. We have all of the online CAD models and simplified prototypes built, but we were unable to build the actual build we anticipated, so it would be a challenge to laser cut the wood pieces and piece all of the pieces together. The conclusions we would like to share with management would be that even though this project was long and timely, the project was really helpful in teaching us how the design process works firsthand. We also really enjoyed being able to finish this project even through the extreme situations.